Welcome to Strength of Materials N6. Today's video is on combined direct and bending stress. I will strongly suggest that you go and watch the video on deflection of beams if you haven't done that already, because we will build upon that. If you do not understand the stuff on deflection of beams, this chapter is gonna seem to be very difficult. But if you understand everything that was done on deflection of beams, then we will pretty much run quickly through this chapter, because there is just about one or two things that I need you to understand, and then you should be able to tackle any question from this particular chapter. So let us begin. Direct stress and bending stress. But before we start with the equations, I need to give you the labels. So M is the letter we will use for the bending moment. I is the area moment of inertia. Sigma D is the direct stress. Sigma B, that is what we will use for the bending stress. Y is the distance from the neutral axis to the point of interest. F is the applied force, A is the cross-sectional area of the beam, and E is the eccentricity. Eccentricity is the distance between the place where the force is applied and is a neutral axis of interest. That is what we refer to as eccentricity. So if you measure the distance between the point of application of a force and the neutral axis of interest, that distance, that is what we refer to as the eccentricity. So let us begin by looking at the direct stress. You already know about it. The direct stress is given by the force divided by the cross-sectional area of the beam. And of course, the unit for that is in pascals, but usually because the numbers are big, we will often use megapascals. Then you have the bending stress, and you know the equation for bending stress. It's equal to the moment of resistance, or the bending moment, multiplied by y, which is the distance from the neutral axis to the point where we're trying to calculate our bending stress, and all of that divided by the area moment of inertia, which is I. And M in this case is also equal to the applied force multiplied by the eccentricity. So when you have an equation for bending stress, the value of the bending moment is also equal to the force that is applied on the beam multiplied by the eccentricity, which is the distance between the point of application of the force and the neutral axis of interest. So let us look at this here. What you're seeing here is a beam, okay? Of course, it's got a rectangular cross-section. We will use that for the sake of explaining, okay? But in your questions, you will not necessarily have a rectangular cross-section for a beam. It can be circular, it can have a combination of different sections. So this is just for the sake of explaining. Do not assume that beams always have rectangular cross sections. So here you have a beam, okay? What you see in blue here is the beam, okay? And on top of it, you have a force F that is applied in such a way that it will compress the beam, okay? Because at the bottom of the beam, of course, maybe we have the ground, okay? So the force F is applied on top of the beam like that, in such a way that it will cause compression of the beam. Now you will know that in strength of materials, both N5 and N6, stresses that are compressive are taken as positive, whereas stresses that are tensile will be taken as negative. Okay, so that force that you see acting on this beam will create compressive direct stresses. So we have it like that. And you can see on top of the beam here, we have a rectangular shape, okay? And this is actually the same as the cross-section of this beam. And we have two neutral axes that are drawn also on top of the beam. You have the XX neutral axis, and you also have the YY neutral axis. And if you watched the video on deflection of beams, I explained that the way we label the neutral axis, which one is XX and which one is YY, is all dependent on which axis is more resistant to bending. Okay, so the axis that is more resistant to bending, that one we will refer to as the XX neutral axis, and the one that is weaker in bending will be referred to as the YY neutral axis. So we have a beam like that. Okay, this is a 3D isometric view of the loading of the beam. And so now, for the sake of explaining bending stresses, okay, we will look at the front view of the beam. When I say the front view of the beam, I mean you looking at it in that direction. Okay, that is the front view of this particular beam. So if you look at this beam in that direction, what you will see is a situation like that. And of course, you will have the force F acting on top of the beam. That's a front view of the beam, looking at it in this direction, okay? And if we try and look at a top view of this beam, what we will see is a situation like this, okay? And this, you will see this neutral axis and that other one. And of course, if you're looking at it in this direction and you look at the top view, the horizontal neutral axis in that case will be the YY neutral axis, and the vertical neutral axis will be the XX neutral axis. And then the force will just be a dot here because it is being applied directly into the screen, okay? Because we're looking at a top view. So that force that you see here, if you look at the top view of this beam, this force is acting at a point, so all you will see in the top view is a point that represents the force that is applied on the beam. Okay, that's very important to understand. And so the distance between the point of application of the force and the XX neutral axis, we will refer to that as EX because it's the eccentricity with reference to the XX neutral axis. And the distance between the point of application of the force and the YY neutral axis, we will refer to that as EY because it is the eccentricity with reference to the YY neutral axis. Very important. And so, if we want to find the bending stress with reference to the XX neutral axis, this is the equation that we will use. And then I want you to notice that the value that we use for the eccentricity is EXX. In fact, it should have been EX, okay? But it's fine, you could label it EXX to say with reference to the XX neutral axis. And then we also have the bending stress with reference to the YY neutral axis, and of course that will be F multiplied by EY or EYY, that's all the same thing, and multiplied again by Y and divided by I. And so what is important to understand at this stage is that as far as the bending stress is concerned, due to this force that is applied on top of the beam, you will have two bending stresses. The one will be with reference to the XX neutral axis, and the other one will be with reference to the YY neutral axis. Again, I repeat, EXX and EX is all the same thing, okay? EYY and EY is also the same thing, okay? Don't get carried away just because of that. And so, one thing that is really important for me to point out to you is that it is possible that a load is applied in such a way that you do not have one of the two eccentricities, okay? So for instance, if this load was applied on the YY neutral axis, so if it was acting exactly in such a way that the point of application of the load was on the YY neutral axis, so it was somewhere on this line, then if that was the case, then of course EY will be 0. The distance between the point of application of the force and the YY neutral axis will be 0 because the load is applied on the neutral axis, okay? So if that is the case, then of course you will not have a bending stress with reference to the YY neutral axis. The only bending stress that you will have will be with reference to the XX neutral axis because you may still have eccentricity as far as the XX neutral axis is concerned. But for you to not have any eccentricities at all, then the load needs to be applied at the centroid. If the load is applied at the centroid, then you do not have bending stresses at all. Okay, no bending stress with reference to the XX neutral axis, no bending stress with reference to the YY neutral axis. For that to happen, the load must be applied at the centroid. So no eccentricities, no bending stress. Okay, that's what it is. Now, let us visualize stresses. It's really important in this particular chapter for you to be able to visualize stresses, because if you can do that, then solving questions on this module becomes very difficult for you. And this is where many people get lost, because they can't picture this in their minds. But I will try to explain it as easily as possible, so bear with me. So this is what we have so far. Okay, we looked at this and I explained this is a front view of that load that was applied there, and on the side of it is a top view, and I explained what the eccentricities are. And so now, for us to be able to understand how to visualize stresses, what we will do, we will try and find the stresses, or rather expressions for the stresses, at the four corners of this particular beam. Okay, so what is the stress at A, what is the stress at B, what is the stress at C, and what is the stress at D? We will derive expressions for those, but the reason we're doing all of that is just to help you understand how to visualize stresses. Okay, so let us begin with the easy one, which is the direct stress. So if you have our load F applied like that, of course, the stresses that you will have will be compressive, okay? As you can see here, the stresses you will have due to this force F will be compressive stresses. So they will tend to shorten the beam, okay? So they go in the same direction as the force that is being applied, and compressive stresses have the same magnitude everywhere on the beam, okay? And to find the magnitude of those stresses, it's very easy. It's the same equation for the direct stress. It's equal to the force divided by the cross-sectional area of the beam. Okay, so for direct stresses, the direction of the stresses will be compressive, and they have the same magnitude everywhere on the beam, okay, and they act pretty much in the same direction as the force. So these arrows that you see here are the compressive stresses due to the compressive force that is acting on the beam. The magnitude of these stresses is the same everywhere in the beam, and they are equal, and it's equal to F over the cross-sectional area. Okay, so that's the direct stress. Now, let us look at the bending stress. And again, I will remind you of the 3D isometric view of the type of loading we're dealing with in this particular question, okay? And so, if we look at the front view, and again, as I said earlier, the front view is what you see when you look at that beam in this direction, okay? That's the front view. If you look at it like that, okay, of course, this is what you're going to see. And I did not draw the full length of the beam. I just sectioned it somewhere in the middle because we're not interested really with the full length of it. We just want to see how the stresses are directed. And so if you look at the front view, what you see is a situation like this. And of course, the top view in this case will be a situation like that. And you will notice in this particular case, I want to begin by focusing on the bending stress with reference to the XX neutral axis. And so if you look at that, what we have here is the eccentricity, EX or EXX if you prefer, which is the eccentricity of this load with reference to the XX neutral axis. And what we see here is the top view of this particular situation. The only thing that we did not draw is the YY neutral axis, because in this case we're trying to find the bending stress due to this force F with reference to the XX neutral axis. And so